Okay, then let me continue the introduction part. So then Professor Gupta has done postdoc from Grenoble, France, between 2001 and 2003. And then immediately he joined in IIT Kanpur as a faculty, as an assistant professor in the year 2003. And since then, he's been faculty there. At the moment, he is a professor there, professor in physics. And he has received an award. He is a recipient of Young Associate Award from Indian Academy of Sciences in the year 2004. So today, Professor Gupta is going to talk about the optimization of niobium µ-SQUIDs. I think it's microsquids for single
Microsquid.
particle nanomagnetism. Yeah, please go ahead.
Okay. Thank you so much, Dr. Sethi, for inviting me and for the kind introduction. So I will discuss our ongoing effort actually, which has been quite fruitful in the recent past on basically optimizing these microsquids for nanomagnetism. So, so this work has been in collaboration with my actually I must say with my postdoc mentor Hervé Courtois and another person in his team, Clemens Winkelmann. And I have been lucky to have many good PhD students. Two of them I am showing here. One is Saurabh Biswas, and right now another one who is about to graduate is Sagar Paul. So we have recently had a postdoc also, Ganesh Kotagiri. And from the French side, there was a postdoc who was of Indian origin, Rini Ganguly. They were there as part of this Indo-French CEFIPRA project. So some funding came recently from CEFIPRA, and there has been some funding from DST through projects. And also, actually, some time ago, I had a CSIR project also on this similar topic. So, so to continue, I start with a basic introduction because I think there are students. So basic introduction to superconductivity. So you have so-called the superconductors, which becomes of zero resistance below their critical temperature. And what sticks out about them is that if you look at the superconducting state, there is it's a macroscopic coherent state in the sense that there are Cooper pairs which go into the same quantum state with a common phase. And then there is certain density of this condensate. So so many Cooper pairs are described by the same quantum wave function. So that is something which is very special about the superconducting state. And what we are going to discuss is basically heavily dependent on this particular fact that there is a macroscopic wave function. So with a coherent phase. So if you look at some typical superconductor, I have listed here two because these two have found a lot of applications. One is niobium, which has a TC of 9.2 K. And there is a BCS gap, which I have not really said much, but I'll skip that. So this TC is around this much, 9.2 and 1.3. Right. So, so there are many other ways of looking at. So this is like this will come from the BCS theory of superconductivity, where you will get gap and everything. But then you can have another theory, which is Ginsburg-Landau theory, and you can learn a lot about coherence length, and you can also learn a lot about how to handle various inhomogeneous situations when you are handling the superconductors, which is easy to do with Ginsburg-Landau theory. So here is the gap. So you have this background density of states of metal, but as you go to the superconducting state, you have a density of states with sharp quasi-particle peaks and a gap here. Okay. So we will not use a lot of these facts much, except for this coherent condensate having the same phase theta. So the Josephson effect is something which is important for the devices that we are going to discuss. So you have two superconductors, let's say, which are weakly coupled. By weakly coupled, let's say you can have an insulating layer in between, very thin, or you can have a coupling through some other means. So we'll see like a normal metal connecting the two, or a very narrow superconducting constriction and things like that. So then there is so the Josephson effect is described by two different facts. One is the DC Josephson effect, where what you see is that there is a supercurrent which can flow through this weak link or the junction, right? And that is a non-dissipative current, so it's a coherent condensate current in a way, and that current depends on the phase difference between the two sides superconductor, or the phase difference between the two condensates. Okay, so that is the DC Josephson effect, and it is limited by some critical current IC, which is determined by how strong or weak this coupling between the two is. So if the coupling is strong, you will get larger critical current, and if it is weak, you will get a small critical current. Now the AC Josephson effect is something to do when you apply a voltage between the two superconductors. You actually end up getting an AC current or AC oscillation in phase difference, which right. So this theta will evolve with time according to this AC Josephson relation. The theta dt will go like 2 EV by h bar, or you could write this also as 2 pi by phi naught times v, where phi naught will be h over 2e, which is the flux quantum. So what you see is that this theta evolves, and if you put that time change evolving theta, you will get sort of an AC current, let's say. And so that is called the AC Josephson effect. Now, if I put the two effects together, so when you take a junction, and let's say you have it biased at some DC current I, okay, and you would like to know what is the energy that has gone in to bring this junction at this particular bias current. So what you do is you take this current I and the voltage V, instantaneous voltage. So the idea is when you are ramping the current from zero value, you will be having a changing theta, because if there is a di dt, you will get a theta as you change the current. Theta is changing. So if theta is changing, there will be a voltage. The voltage is governed by the AC Josephson effect. So you put the two relations together and integrate this guy. So I will be IC sine theta, and V is basically phi naught by 2 pi times d theta dt. So you integrate out, you get something like this. So the energy of the junction will depend on the phase across the junction. So if theta is, let's say, 0, then you get 1 minus cosine 0, so 0 phase, so 0 energy. And but if you have finite theta, you will get, of course, certain energy associated with the junction. So the prefactor here is phi naught IC by 2 pi, which is called the Josephson energy. Okay, so this is the Josephson energy, which is determined by the strength of coupling. And if this energy is large, if IC is large, you will get large Josephson energy. And if you are a small IC, then this will be very tiny. So the consequence of this whole thing is that if you work with a junction with very small IC, then the thermal fluctuations can wash out the Josephson effect completely, in the sense that thermal fluctuations will cause a lot of these phase fluctuations, because the system is not so robust with respect to the phase fluctuations, and you will wash out the Josephson effect completely. So seeing the Josephson effect with a small IC is not that easy, right? You will have to do a lot of noise isolation. So the idea is, in case if you want to have a junction with observable Josephson effect, then you should be working at this kind of condition that IC should be greater than certain 2 pi kBT by phi naught. So few microampere at 4.2 K at least. Okay. Now, the one of the consequence of this kind of IC requirement is that either you make these Josephson junctions very thin to get a good coupling, or you make these junctions large in area. So both of these thin or large area will lead to a larger capacitance associated with this junction. Okay, so if there is a capacitance associated with the junction, there is some consequence of that, and that consequence is hysteresis in the IV characteristics of the junction. Okay, so you get this hysteresis in conventional SIS junctions, which one has to then find ways to eliminate in order to use Josephson effects in the squids for magnetometry applications. Okay, so there is a way to do that in case of conventional Josephson junctions, where the origin of hysteresis is the capacitance. Okay. But then, of course, you have certain benefits also of this large capacitance and so on. So that is more towards the quantum applications of Josephson junctions. So that is right. When you look at the using these junctions for qubit applications, you want a minimum dissipation and a reasonable capacitance. Anyhow, so going towards the squids now. So you can interrupt me if you have any questions at any point of time. Please feel free to do so. SQUID, which is superconducting quantum interference device, it consists of two such Josephson junctions in parallel. So you have sort of a loop interrupted by two junctions. And when you have a flux going through this loop, right, you will see that there will be a phase difference. So if you do some sort of this Aronow-Bohm like physics where you account for this overall phase across this loop, you will see that theta 1 and theta 2 will differ by the flux threading through the loop. So flux in units of flux quanta times 2 pi. So if you use this fact and the fact that the total current has to be basically the current through this junction plus that junction is this, you can take a simplification of two identical junctions and you end up with total current which will have this kind of form. So there's like average phase drop across the two junctions. And then you have this prefactor which is dependent on the flux through the squid loop. So you get a non-monotonic IC. So this is the effective IC, which means when you change the total current, this theta is a free parameter which is decided by the junction, but it cannot take values beyond the range 0 to 2 pi. So you are limited in terms of the bias current, or the non-dissipative current will flow only determined by this amplitude, which is dependent on the flux through the junction. So what you see is that this IC total as a function of flux shows you this oscillatory behavior. Okay, so what you will see in this case is if you go to a integer flux quanta value of the flux through the squid, you get maximum IC, which means the IV characteristics will have a form like 0 to IC. You see no resistance, no voltage, and suddenly there is a jump in voltage and you see this behavior. And then at the same time, if you go to a different flux value, IC is small, so you will come here. Okay, So you can imagine that it's rather tedious if you have to use this, because it's the IC which depends on the flux and not the voltage, strictly speaking. Okay. So anyhow, going forward, so realistic, right? So when you look at a actual MPMS system, so-called magnetic properties measurement system, it actually works using, like, so you couple your samples flux through a big loop, which sort of has an terminates into an inductor, which is lying very close to the actual squid. And so this is actually a superconducting wire. And so whatever is the flux change because of the sample, that is reflected here in this inductor, and that couples to the squid. So very indirectly, you are able to sense the magnetic properties or magnetization or of the sample through the squid. So the sample can can be quite far, and it can be at a different temperature. So all you need to ensure is that this squid loop, this superconducting loop is kept superconducting, and the squid, of course, works only when it is below TC. So it is worked actually. It usually is operated in a feedback loop mode because of the peculiar non-monotonic transducer property, because you see the dependent on flux of IC is non-monotonic, it is oscillatory. So what one would do is you sort of come to, let's say, somewhere this point, and you keep this as an operating point, in the sense that you have another coil which gives some flux to the squid, and squid actually acts as a very sensitive flux nulling device. So you make sure that the total flux through the squid is kept at a constant value, so that its critical current is same. So when the flux changes, the critical current changes, and that is reflected by changing the current in this inductor. So there is a feedback which changes the current of this inductor very fast, so as to maintain the critical current value the same. So this works in a flux locked loop mode typically in these commercial systems. So you can see the actual geometry where you have a modulation coil, which is this one, and this is the other coil which brings the sample flux, and this is the squid washer here. Okay, so this is the way these things are operated in commercial setup. So now I come to the hysteresis a little more, because hysteresis is a problem. So what happens is, okay, sorry, I have not introduced the meaning of hysteresis yet, but let me say a little bit here. I'm sorry, I don't have a slide on that. So the idea is, if you ramp the current, the critical current is reached, and you reach a finite voltage state, and you go to a sort of a resistive branch. And then when you reduce the current, okay, to come back to the zero voltage state again, it actually, the transition doesn't happen at the same current, it rather happens at a lower current. So that is called the retrapping current. Okay, so this is the kind of hysteresis we are talking about, which makes life very difficult, because for flux sensing you have to measure this IC very precisely, and if there is hysteresis, you have to ramp this current this, and then you have to ramp it down below IR. That is one measurement, so it will slow down the whole thing a lot. So you need to right, I mean, so that is not desirable. So anyhow, so how do you understand this hysteresis? That is the first question in the conventional Josephson junctions. So if you look at, so there is a model called RCSJ model, where you take a Josephson junction, right? As I said, there is a capacitance associated with the junction, because it's actually made in a capacitance geometry, where you take a superconductor layer and then an insulator on top, and then another superconductor. So that's a nice capacitor geometry. And then you will have some resistance. So resistance, I am considering in this context, can be even an externally put resistor, okay? Or it can arise from the quasi-particle resistance basically across the junction. So I will not say too much about that right now unless you want to know more. So if I put simple this current sharing Kirchhoff law equations, basically the total current is I, which is shared between the Josephson junction, the resistor, and the capacitor, okay, CdV So there is the AC relation we have. You use this to eliminate V, and you write this equation purely in terms of the theta dynamics. So you get this equation in second order because of dV dt, which is giving you this thing. So anyway, so you get C phi naught theta double dot, and then this term linear first derivative, and then right hand side is this. So you can satisfy that this equation leads to this one. And then you can recast this equation in another way, that is here. Okay, so theta dot term, and the right hand side I write at some sort of a theta derivative of a potential energy, which I call minus del u del theta. So the same this equation also arises in a very interesting mechanical system, which I show here, which is very insightful if you connect it with the Josephson effect. In the sense, you take a simple pulley and string and mass here, and then but there is a load mounted on the pulley which is fixed to the pulley of which is fixed, so this load will rotate with the pulley. So the idea is when you put certain mass here, this guy will take an equilibrium angle theta and it will stay there. But so this, you write the equation of motion, and I can tell you it is exactly same except for this damping term. So you can dip this whole system in some oil to get the damping also, and then this describes this equation completely. Okay, so in this case what happens is that I is like the mass, this mass here. So as you increase this mass, this will come down, and there will be a critical mass above which this guy will just keep going down and down and down. There is no equilibrium theta, and this guy will just keep unwinding and rotating and rotating. Okay, so that is precisely the kind of dynamics we are going to have associated with this equation. And so if you want to capture it using this u that we just discussed, you end up with this potential, which is oscillatory because of this theta term. So you see this oscillatory cosine, but there is I term here, which is the bias current. So you have this I over IC theta, which gives you a slope or a straight line added to the cosine theta. So you have some sort of a model, this potential, which is called tilted washboard potential in the context of RCSJ model. So this tilted washboard potential basically describes the dynamics of this phase variable quite nicely and captures the hysteresis also. Okay, so just to tell you a little bit about how the hysteresis is captured is when you tilt this washboard, this guy will stay in one of the local minima unless you exceed the slope, right? So which will happen at I equal to IC, then these minima disappear, and then this ball starts rolling down the hill continuously, right? So that is the condition at IC. So at IC or above, you see that this ball is rolling down continuously, which means theta is going to change continuously with time, which means theta dot is non-zero, and theta dot non-zero means there will be a finite voltage across the junction. So you get a voltage state now above IC. Now you tilt it back, you will tilt it back, but you will see that it doesn't stop at the same IC because of the inertia considerations which come from this term. So this is like competition between inertia and drag. So if the inertia is large as compared to drag, then this guy will keep rolling down because the loss in energy is not much. So when it rolls down, let's come to this one particularly. So what will happen is it will gain some energy when it rolls down here, but it may not lose the same amount of energy when it goes up there. Okay, so if it doesn't, then it will just simply keep rolling down and down and down. So you don't get away from the dissipative finite voltage state, even though you have reduced the current to below IC value. Okay, so this describes the hysteresis. It is coming from some dynamic considerations. So what you see as the IV characteristics is that this IC here, and then this is the IR. So there will be certain current IR which will be decided by the competition between the how much energy it is gaining versus how much it is losing due to dissipation. So the dissipation will play a role in that. So the second term, right? So depending on that balance, you will find a current at which there will be like balancing, and then above that, below that current rather, the system will find it settled in one of the minima. So that is your IR. Okay, so this is the physics of hysteresis, if you like. And so if you want to look at now the role of this resistance, right? So you put a small resistance, let's say by hand, so that will lead to large dissipation. And if the dissipation is large, then you can imagine a situation where this role doesn't play much role. This term play very little role because R being very small, large dissipation, and then this guy will move without the effect of inertia. So in that case, you can imagine that it will give you basically a reversible curve, which will have a shape something like this. Okay. So this is the sort of the condition you can think of. Okay, what will be the no condition for non-hysteretic setup, and then you can get the value of R that is desirable. So there is a parameter called Macomber parameter, which sort of captures the threshold value of beta, which is required in order to get away from the hysteretic state. So here the bottom line is the resistance will help you get rid of the hysteresis. Now we come to, right, so I am working with micro squids, very small size squids, which are micron size. So typically in conventional squids, the junction side is quite large. So you cannot reduce these squids very much in size because you need to have a significant critical current, as I said. So in order to make the squids small, what is done is, you rather than making SIS junctions, you make something called these constriction type weak links. So you have, let's say, this niobium pattern which you washer like, and you make very narrow constrictions here which act like Josephson junction. So this can be justified if you do a little bit of Ginsburg-Landau type theory, which is you could review if you like this physics in Likharev's review paper of quite an old one. Okay. So this also leads to a very similar Josephson behavior. If you look at a constriction which has a size which is comparable to or less than the coherence length is I. So you have to work with rather small constrictions if you want to have close to ideal Josephson junction like behavior. Okay. Anyhow, so we see that Josephson behavior in such things. Okay. Let me skip for this one for now. So anyway, what I wanted to say in this slide is that if you look at these constriction type Josephson junctions, you still have hysteresis. In fact, you have large hysteresis. So this is the hysteresis in some such weak lengths. You see the IC is huge and IR is so much less. And so this is a problem in this case. But in this case, the capacitance is not really the reason, because in these devices, the capacitance is rather small. So this is very small constriction. So if you look at the geometric capacitance, it's actually negligible. So that is right, a more realistic Josephson junction. The squid, micro squid, I'm showing here. So this is like very small size. This is like 1 micron is the inside area. So the geometric capacitance is very small. So you can't blame the capacitance for its hysteresis. So the real blame for hysteresis goes to the thermal heating effects. Okay. So the reason for thermal heating effects, I have reviewed a simple toy model here. Okay. So this toy model is something like you take, let's say, two bulk superconducting electrodes, and then you have this sort of a weak link, which I show a elongated wire, a little bit exaggerated. Anyhow, I maintain that two superconductors at some sort of a bath temperature, and then I imagine a situation that if I somehow end up with a state where there is a hot spot, which is hot meaning its temperature is above TC, okay, and the rest is superconducting. So this will lead to a resistance. And if this is resistive, then the current flowing through this weak link will lead to a resistive heat generation, I square R. And that heat generation will have to be, so the heat has to be evacuated. So there is a steady state temperature profile which will arise, right? So this guy will lead to a heat generation and then heat evacuation here. So so that means there is a self sustained hot spot which is there, which will lead to a voltage state. Okay, so what this means is that you look at this heat dissipation, right? So you have this heat generated here, and then the heat conducted to the side electrodes. So very simple situation. I'm saying that the heat is evacuated only to the side electrodes, and you put everything together, you get a condition for this self-sustained hotspot, which is x naught times L minus x naught, equal to this whole thing, which is lambda over I. So lambda is a constant, let's say, which depends on the material parameters and the geometry, and the I is the bias current. So you look at this guy, you plot it. So x naught L minus x naught is inverted parabola. You put these straight lines for different current values, you get the solutions for x naught, right? So you see that as the very small current, this guy will become large. So when it exceeds this point, you get to a non-self-sustained hotspot state, which means that the system will come to the cold state, right, below this current. But above this current, you have a possibility of having this hotspot state. So this is so-called a static hotspot model, where I call it static in the sense that this temperature takes a steady profile. It's not changing with time. Okay. So and then you can see that there will be, okay, as you reach IC, suddenly there is heating at IC in the weak link, and you get to a resistive state, right? And then this hotspot is created when you reach IC, and but when you come down below IC, the hotspot will self-sustain until a current IR, and that's when this becomes not possible to sustain. So this is the sort of simple picture of this whole IV characteristics. And then you can also see something that this, sorry, retrapping current has no dependence on the superconducting properties, which means that this is dictated by purely the thermal aspects of the problem, while the superconducting critical current depends on the superconducting properties and cross section, etc. So these are two disconnected currents, in the sense the physics of the two is dictated by two different things completely. Right. So, so this is right. So the idea is, if you can sort of bring this, make this current up, retrapping current higher and higher, so that it becomes greater than IC, then you will get to a non-hysteretic regime, possibly. Okay. So, but that is not an easy task. But this model misses something completely. Okay, so that is what I want to stress here. It misses something completely. And we realized it when we did several experiments. So this is one of the experiment we did, right? We published in PRL in 2015. So what we see is that we look at a simple squid device, and so here we had a device with rather long leads, and so there is also some short leads, and then there is a squid loop with these constrictions. Okay, so this device we did not plan that very well. I mean, we planned it, of course, with some things in mind, but the kind of things we saw were completely unanticipated. So what we see is, when you look at the IV characteristics, we see an IC, okay, and then there is a jump. Then you reduce a current. You come here, here, here. Then there is another a jump, but not, it doesn't go fully to the superconducting state. As you reduce current further, it goes to the superconducting state at a much lower current. So there are two different retrapping currents that we identified, IR1 and IR2. And then eventually it goes to superconducting state. Okay. Now these currents evolved heavily with temperature, with the bath temperature. So as we raise the temperature, we see that this IC becomes smaller, and it approaches IR2. So it goes to IR2, and then even little more raise in temperature, it actually crosses IR2, which means that this part of the IVC now is non-hysteretic, right? So this IR2 sticks out anyway. And then you get a hysteresis, a smaller hysteresis loop, which you further raise the temperature, the ICIR1 approach each other. And then as you go to certain temperature, in fact, now we see that, okay, the IC has crossed IR1, and then the thing is completely non-hysteretic. So this helped us learn quite a bit about this such devices. In the sense, we could say from the resistance values exactly what portions of this device were actually normal, meaning non-superconducting. So for example, we found that if you look at the resistance value right above IR2, it turns out that the device from this end till this end is actually resistive, meaning this whole portion is normal. Okay, right? So the heating effect is so significant in this case, and it is self-sustained. Okay, so that is one part. Now you reduce the current right down, and then you come to somewhere where only this portion is hot. Okay, and then at IR1 suddenly it collapses, so the everything becomes superconducting. So we realize that, so we have discussed in this paper something about the static bistability of the NS interface, where it turns out that if you have a current carrying superconducting strip on a substrate, then it can have a NS interface somehow, okay, which is the case here. Then the NS interface will have an instability in the sense that it can move either this way or that way. Okay, so it turns out if the current is larger than this much, then the NS interface would run towards the superconducting side. And if it is smaller than this, then it will run towards the normal side. So that is what is happening. So as you cross this threshold current, this NS interface was here above this IR2, and then suddenly it jumps towards this. Okay, both sides. Okay, so you see it gets pinned here now, and then there is the similar physics of the NS interface. It will eventually come here. Okay. Anyhow, so you look at these various currents, and you realize that this is we could understand the temperature dependence of IR2 as well as IR1 to some extent, and then how IC crosses them, and eventually it becomes non-hysteric. So this helped us understand things quite a bit. So we had similar another device where the constriction size was different, so critical current was lower. But then we saw that IR2 and IR1 are more or less same as the other device, but IC changes. So if IC is reduced, you see you get a wider range of hysteresis-free operation. So reducing IC is helping in terms of eliminating hysteresis. There is another thing which we argued, and that is the title of this paper. Is basically you see there is a drastic change in the temperature dependence of the critical current, that it is coming down linearly, and suddenly when it crosses this IR1, it changes the dependence quite a bit. Same thing here. Okay, so apparent TC of this constriction is somewhere here, but the TC gets pushed up to here because of the inverse proximity effect, which means that the intrinsic TC of these weak links, because they are very narrow, and therefore there is enough oxygen contamination, and niobium is known to be very sensitive, that its TC changes quite a bit if you make different size devices of niobium. So different portions will have different TC, but then this wider portion is supporting the superconductivity in the weak links. So which means that through this inverse proximity or proximity of the superconducting leads with higher TC, you can support the critical current up to a higher temperature in this case. Okay, so quite a few facts we learned from this exercise. Another thing, we looked at the squid oscillations. So we don't see any squid oscillations in this heated portion at all. So this also confirms that whenever this loop is hot, there is no coherence left, and there is no response to voltage to the flux in this regime. You see the response of voltage to the flux only very close to this regime. Okay, so this gray regime we see some response. So IC of course shows clear response, right? So because in IC the thing is still cold, but as soon as you jump to the resistive state, everything is hot, so no coherence left. So you see the IC oscillations, not very good quality, okay, for various reasons. But you see voltage oscillations with the flux in the non-hysteretic regime, very close to the TC. So when you come here, one sees this oscillation. So this is what we actually want. If we can directly see the voltage oscillations with the flux, then we can use this as a very nice transducer for the magnetic detection. Okay, so that is, but these oscillations lasted over very narrow current range. So we had problems in understanding this part, and that's when we were thinking about better ways of understanding these devices. So we asked a question that suppose we optimize devices, okay, to remove static thermal instabilities somehow or the other, then what behavior to expect? Should we go to RCSJ or hotspot or whatever else? So this is the question which led to this model, which has helped us enormously, as it has guided us further to come up with ideas to optimize these devices, as well as it has helped us, discover some new regimes of physics in these devices. So, so this is a simple model, though. So it's basically an RCSA model, but it is slightly modified because there is no capacitance in these devices that we have. So what you see is this RCSJ type current sharing between the Josephson channel and the resistive channel of the weak link. So the idea is we are working with some sort of a two fluid model in this sense, in the sense that this current can flow either as coherent Cooper pair current, or it can flow as resistive current. So this may happen that when the current is being when there is a resistance because of the phase dynamics, right? So sorry. So that when so okay, let me slow down. So the idea is if there is a voltage across this junction because of the phase dynamics, then the voltage will inevitably lead to a little bit of linear normal current, and then there is the supercurrent. Okay, so it's a basically similar relation. So this is coming from the DC shearing. Then there is AC Josephson relation, which is valid in all sorts of weak links, by the way. And then we have a temperature description of the weak link itself. So where we simplified things to the extent that we look at the weak link region's temperature, and that temperature will evolve depending on the dissipation because of the voltage in this region. And then there is a heat loss to the environment through some sort of a either interface or something or the other. So there is a simplification in this sense. So there's a linear heat loss depending on temperature of the weak link and the surrounding bath temperature. So that is the case, some sort of heat loss coefficient. And so this is the heat loss to the surroundings, and this is the heat generated because of the V square by R heat, and R is generated only because of the Rn, because so Josephson is non-dissipative. And then this is basically the net heat accumulated in this region, which will tell you the temperature rate at which the temperature changes, together with the heat capacity of the weak link. So one can actually simplify this and put them into some sort of a dimensionless form. So this forms some sort of a dynamical system with two parameters, phase phi and the temperature, which I write P here. And so P is defined here, which is T minus TB over Tc minus TB. And then I define this thermal time, which is CWL by K. So this is very important for our system. And then there is a Josephson time, which is the flux quantum over the voltage at the critical current. Okay, then then we define this parameter alpha, which is the ratio of thermal time and the Josephson time. Now, beta is a parameter which turns out to be very, very important for the dynamics of this system. So typically, alpha is very large in the sense that the thermal time is much greater than the Josephson time, but beta is still there. Okay, so if we work with this large alpha approximation, we can solve these equations even somewhat analytically. Okay, and so this is anyway a numerical solution. So you see that this is the phi dot, the phase changes a lot, but the temperature sort of temperature rises above the equilibrium value, the P equal to 0 value, but it settles at varies almost the same value. So there's the temperature change with time is very small because this is amplified by a factor of 1,000. Okay, so real temperature change with time is very small, and from P minus point. So it's very almost like 0.61. It is settled at 0.61 with little fluctuation. So this is the approximation I'm talking about, that when alpha is a large number, you can make a simplification that, okay, P is more or less constant, which is the case, and only phase phi will change with time. Okay, so anyhow, you solve this system, you get hysteresis. You get hysteresis in a very different sense, and that hysteresis is precisely the dynamical hysteresis, which is more like the RCSJ model hysteresis, although there is no capacitance anymore in this case. So you see this hysteresis in this, right? So, and in fact, in this case, both IR retrapping current and critical current, they both depend. Now I have actually, okay, so this dynamic retrapping current and the critical current, they both depend on IC inevitably. So now these both are somewhat connected to each other, okay, through superconductivity. And so these are the currents which I discuss. So IDR and the IC. So what you see is that this IC goes linearly to zero at TC, and the retrapping current sort of approaches zero, but it stays always below IC, which means things will always be hysteretic no matter what. So you can't eliminate hysteresis just like that. That is what it says, even though you don't have any capacitance. So this was the model, and there are several other aspects which I will skip right now, which is like, so this ISR is another interesting thing. This is actually the current at which the weak link becomes normal. So as you increase the current, although there is coherence, so there is a current which is shared between the superconducting branch and the normal branch. But as you exceed this current ISR, the coherence is lost. So you will not see any coherence effect, which means no flux oscillations, no squid behavior will be seen beyond this current. Okay, so this is another thing which is coming out of this model, right? And then you have only a limited range of current over which you will see this coherence, and that limited range depends seriously on beta. So if beta is large, you have very little range. If beta is small, you get larger range of coherence available for exploiting for the magnetic sensing. So this was the idea of this. We call this as DTM, the dynamic thermal model, and so these are the consequences, which is it's somewhat like RCSJ but without any capacitance. So it's only thermal effect, and you can think of thermal time is sort of like the capacitive time in this case. So we actually then started looking for this dynamic thermal regime, and we saw it, okay, very nicely in some of the optimized devices. So how you interpret, we see it is that IC oscillates, but more than IC, actually the retrapping current shows very clear oscillations, which means there is coherence when you are reaching the retrapping current, which was not the case in earlier devices, so which had a relatively high IC. The IR had no response to the flux at all. So, but here we see a very clear response to the flux for both IC and retrapping current. And then you have a non-hysteretic regime also, where you see the voltage oscillations very clearly. Okay, so these are the voltage oscillations if you go to the non-hysteretic regime, but non-hysteretic regime is tricky. So that is something I don't know if I will get too much time. Anyhow, I think I am running close to my time. I will continue. I hope you are able to listen to me, right?
Yes, yes, yeah. We are listening to you.
Okay, thank you so much. So yeah, so the idea is, so this device, this result we published, this we struggled with referee for a year actually to get it in PRL. It went to referee and 2-3 iterations. One of the referees we could not convince, so eventually it went to PRB. But when it came to PRB, it was within 24 hours that the editors agreed to accept it PRB. Anyhow, so the what is critical thing is that the DTM, the our model fits quite well for this supercurrent part of it, while RCSJ has no match. So which is basically sort of saying, okay, there is reasonable truth in this model, and we should be actually sticking to this model when we are looking at such devices. Okay, so we did a little further to optimize. So we said, okay, let's try to put a resistive shunt and see, just like RCSJ, how it changes things. So it turns out it simply changes beta, and you will get actually the non-hysteretic regime easily if you put a resistive shunt close enough to the weak link. But the resistive shunt, the good thing is that a lot of heat will be dissipated within the resistive shunt, which will not be seen by the junction. So that's a great thing, that you evacuate some of the heat, you channel the heat away from the junction, and junction behaves better and better that way. So we see reduction. So this crossover where the non-hysteretic regime starts, the temperature changes to lower and lower value as you put smaller and smaller shunt resistors. Okay, so that we could see. So now I come to another interesting consequence of this model only. So this model, as I said, if you look at this IC and IR dynamic, they merge, they never actually cross over. So it's a funny situation. Okay. So what is happening actually, if I go into details of the dynamical system, there are two states which appear in the dynamical system, which are given by some sort of a potential like this. So you have two minima, one here, another here, which evolves with the bias current. Okay, so if you change the bias current, the system will preferably go into this heated minima, high temperature minima. And as you lower the bias current, this minima eventually disappears and it rolls down to the zero temperature, 0P minima. So this otherwise there is a regime where the two minima coexist. And as you change the temperature, the minima, the barrier between the two minima will become less and less, and the system will become more fragile to spontaneously jump between this minima and that minima. So that is precisely what I show here. If you go to very close to this so-called apparent merging point, but this is only apparent because they meet only at 1. So if you go very close, you see this bistability in the RT as a random switching between the two states, the superconducting state and the finite voltage state. Okay, so this was interesting. So we decided to do a little more. Actually, there was this lady, Sudeshna Sinha, who came and delivered a talk, a fantastic talk on the stochastic processes in bistable systems or so. So then we learned that there is some phenomena called stochastic resonance, which exists in such bistable system. And this our system looked like an ideal system to look for something like this. So this is precisely the experiment we did. So we probed, so these are like the IV characteristics. As you change the temperature, so this is like clear hysteresis, and then there is like jumping back and forth. As you go higher in temperature, it becomes more and more smooth. Okay, so the idea here is that as you increase the temperature, the system is more fragile in the sense of switching between the two states, and actually it switches between the two states at a higher rate. Okay, so higher rate meaning, so you will get an average over voltage between the two states depending on how much time the system spends in either of the two states. So that's the idea, that you will see that the system will be much less in the high resistance state here, but if you go to this point, it will spend much more time in the high resistance state, right? But if you look at the actual time series, you will see this behavior with very little things, so the time, actually I should have put that plot, which I don't have here. Anyhow, so the other thing which you see is the standard deviation. So each voltage that we have acquired here is actually an averaged over voltage over some finite time. The same averaging, we can also calculate the standard deviation. So you see that the standard deviation is actually peaking, okay, because of this random switching. As soon as you go away from the random switching regime, you see a flat either here or on that side. Both sides it's flat, no random switching. As soon as you go to this bistable regime, you see random switching and therefore large standard deviation in voltage. In fact, this, if you look at this voltage deviation sigma v square as a function of the average voltage, right, it's actually a parabola. Okay, so this, you can fit this guy and it fits beautifully as a parabola. Okay, so because it's a bistable, it's only two state, so we get something like this. So this works out nice. Now what you can do is look at the same thing in the the random switching in the Fourier domain. So you take Fourier transform, which is basically taken by computer, and then you plot this Fourier spectrum at different temperatures. So we do that at the midpoint where the voltage is like we are right at the peak of the standard deviation. So that means we are at a point at a bias current where the probability to be either in either of the two states is 50-50, half half. Okay, so we carefully go to such a point and then do all the and measurements that we analyze further. So you can see that this is the so-called the Lorentzian shape you get out of this RTN, which is very well understood in case of RTN with certain cutoff frequencies. So if you scale the frequencies together and put all of these curves, they come pretty much on top of one universal Lorentzian. And this frequency, so-called, which is a parameter which is temperature dependent, this frequency changes rapidly with temperature. So at high temperatures, the frequency is rather large. Okay, so and at low temperature the frequency will be small, which you can see here also. Okay, what sticks out in this case was if you now drive the system with an AC modulation, AC current, so you see that the response, the AC response as a function of the drive frequency. Okay, so what one sees is you see a peak in the response whenever the AC drive frequency matches with the internal switching scale, that is FC, which is actually a random thing. Okay, the switching between the two states is random, but there is a time scale associated with it. Okay, because the barrier crossing, when it happens, you have right. I mean, it is a random process, but there is a characteristic time. So then whenever this deterministic drive time scale matches with the stochastic switching time, you see an enhanced response. Okay, so this is precisely the philosophy of stochastic resonance, that you have like two time scales. One is random time scale, the other is deterministic. When they match with each other, you see a large response. Okay, so this has implications for sensitivity, signal to noise ratio, and everything else. And eventually we see the same thing in the squids. So this was single weak link, and then we did this for the squid, where we actually drove, rather than the current, we drove the flux of certain frequency, right, very small, and we see exactly a very similar peak in the response as a function of this temperature, which matches with the idea of stochastic resonance. So this was very nice, which we could actually eventually get to because of our understanding with this dynamical model, I must say. Okay, so I think I will now run through things fast because I have taken too much time. So we did some effect of inductance also. So if we put an inductive shunt rather than just a pure shunt, as I discussed earlier, so inductance bring its own time scale which competes with the thermal time. So the system becomes a little more complex, and you solve this system, and we did solve it, and we came up with some predictions which matched fairly well with the experiment, which gave us more confidence on this simple model. So we can actually, it turns out that even with a if you add inductance, then you can eliminate hysteresis more cleverly, and that was the sort of the bottom line, because this inductive time competes with the thermal time in a very funny way. So funny way, when I say there is a bifurcation which we learned in this dynamical system. It is called Hop bifurcation, which occurs if you solve this system, and that leads to this elimination of thermal bistability over a wider current range than what is there over a wider temperature range than what is there only with the resistive shunt. So this was something which appeared in PRB after some. So Right. So finally, the last punchline, Microsquid Magnetometer. Yes, we have set it up. So with a vector magnet and everything else. And we have characterized some magnetic nanoparticle structures. So one is this paramalloy nanowire, where we look at the anisotropy. So we look at it with the both hysteretic as well as non-hysteretic microsquids. The magnetic behavior, of course, is similar, but non-hysteretic gives us much cleaner data as compared to the hysteretic squids. So this is the anisotropy of this paramalloy nanowire studied with this our squids here setup. Okay, and then we have characterized some of these Fe3O4 nanoparticles for their magnetic properties. So this is something, right? We see this MH loop, but there is something more interesting which we are reporting now, uh, which is to do with the switching statistics of these particles. Okay, so this is I don't think I have time to go in great detail, but here the switching happens mainly through this vortex entering. So this is like vortex entering here, then vortex goes through the particle, and then suddenly it annihilates here. Okay, so this is the micromagnetic simulation which shows this kind of behavior. So here the statistics is more interesting. So well, I think I should let me say some things if nobody is speaking anything. So so the idea here is that that as you go close to this switching field of this vortex, right? So if you wait there, eventually it switches. So these guys, although they we are here, we are sweeping the magnetic field, but actually the sweep, when we sweep, the histogram of the switching field are not are kind of narrow. So but here you see this is like the histogram of switching field. So you see there are two switching fields in fact, and in fact there are two ways the thing happen. That one way, if you track, it goes this, and then there is one switching field. If you track this one, then this is going this way, and then there is other switching field. So this is right, some sort of a bifurcation here. So this switching events in ferromagnetic nanostructures are rather complex, as we have learned through micromagnetic simulations. But so this is one part. But what is more important is that if you zoom in, these histograms are quite narrow, a millitesla or so. And when we go to, let's say, this field and wait here, let's say, so as we will have some probability of switching, or rather we will have it, we wait some time and then we see at some point of time it switches. So we see, we collect these switching statistics data and see, okay, what is, how does the probability of seeing a particular switching time at a particular field, right, changes with field. So these are some of these data which show that, okay, the histograms are more described by multiple times, and it's not a stretched exponential, it's closer to compressed exponential behavior. And then we best describe it using, like, three multiple barriers in series. So this is something which we are yet to submit a manuscript on. Okay, so so this is the summary, and thank you so much.
Thank you, Professor Gupta, for the nice talk and especially showing us the new design. I mean, the design of microscripts. So the talk was really interesting. So now the talk is open for the questions. So if there are any questions, you may please ask. Yeah, Priya, please go ahead.
Yeah, and then nice talk. So I had
Thank you.
few basic questions. The thing is, yeah, one sec, let me put
Should
my
I go to the earlier slide?
yeah. So for the last question is, I mean, you just showed some data on Fe3O4,
Right.
and you talked about the barriers. So what exactly do you think are the origin of the barriers? That's the
So, well, um, generally speaking, there is a barrier coming from this vortex. So the idea is vortex, when you are close to this threshold, the system has two states, sort of metastable. One is that where there is no vortex, and the second is where the vortex is here somewhere. Okay, so both are energetically possible. That's why there is a bistability or hysteresis. Okay, now these two states are separated by a barrier. So there is a barrier which is because of the magnetic regions which will come from various considerations. I think it is quite complex to say too much about it.
Okay.
Okay,
Okay.
but then what I am trying to say here is, so there is a broad such a structure of a barrier, and so there is a, let's say, minima, maxima, and then there is a deep minima, and the system is trapped in the shallow minima. Okay, now we are waiting at the shallow minima. There is a finite time it takes to jump from this to the deeper minima. So this is the statistics we are looking at effectively. Okay. Now it turns out actually there is no single minima. So this landscape is not all that smooth as I am imagining. Actually, this has several little minima or several little pinning centers for the vortex, where the vortex gets pinned before it gets completely lost.
So could that be related to defects present?
It is defects. It should be defects, but yeah, I believe it is defects. So surface defects or something. So that's why, I mean, it's like, the histograms for switching times becomes very sharp actually. So the idea here is, as you go to a field which is very close to switching field, you can explain these histograms by a single time scale. So this is like a single barrier. But when you are going away from it, you need, I think, 2 or 3 time scales or 2 or 3 barriers in series, not in parallel. So this is something remarkable, that most of the time you see that the histograms becomes stretched exponential, where you explain it easily based on that multiple channels available in parallel. But here it's more like there is only one channel, and that channel has many such little barriers which it has to cross in order to go all the way.
Yeah, and the other thing I had, I mean, it's a very basic thing. So you went to, in the first model, you said, like basically you had, I mean, the way I understood it, there was a thermal hysteresis you spoke of. And in
Right.
that case, you didn't have the Josephson junction oscillations. You didn't have those oscillations.
We did not. So
Yeah.
once you go to the voltage state, you don't have any oscillations. That is consistently we saw.
So the thing is, the I mean, the explanation is that locally it's heating it up and taking it out of the superconducting region. Is that what you're trying to say?
Right, right.
Okay,
So
okay.
that was the static model that this that so this is a model which was earlier. I mean, so you see, this is an old model which was originally Skocpol, Beasley, and Tinkham model, 1973, where they look at this hotspot formation in constrictions. And so this, like, so this whole superconducting region, anywhere if it heats up above TC,
Okay,
the
okay.
coherence is lost.
Okay, okay. Yeah, and then the second part where you had, I mean, I don't remember the names, but you said that there's no capacitance. But I thought that anytime you have this kind of two superconducting and
Right,
middle insulator, you do have a capacitive thing. So
right,
what is the
right.
reason for
But this
neglecting?
capacitance is
Yes.
very tiny as
Okay.
compared to the conventional junctions, where the capacitance can be like picofarad order. Here it will be more like attofarad.
Is this because of the length of the making the length the separation larger? I mean,
No, the overlap is right. So remember, earlier junctions are sandwich like junctions.
okay, okay.
The conventional Josephson junction, you have a superconductor, you put insulator, and then you have another overlapping thing.
I see. Okay, okay.
So that is this is a clear capacitor. But
But
here you don't have such overlap. It's only a lateral junction.
okay, okay. I see.
So there is no capacitance. I mean, very negligible, if at all.
Okay. So that should be true even in the previous one which you showed, right? Where you had Like, because your constriction was similar in this previous.
Right. So this all, yeah, very much.
Okay.
But it's just that we were in a regime in this, so we were convinced that we are actually having his thermal hysteresis, okay? And we were thinking of that Skok-Pol model at that time, okay? Because we were not close to stabilizing this dynamic regime. Dynamic regime is observable only when you go to a parameter regime where beta is significantly small. If beta is large, which was the case with most of the earlier devices, the beta was very large. So we get almost no dynamic regime.
Okay.
You understand? Here you see very little dynamic regime.
Okay.
But if you go, so then we, with this model, we were looking for devices where beta will be significantly small. So we get an observable dynamic regime, which we do get. So that was the thing about this model, that you see that we are in the dynamic regime where even at finite voltages, you have coherence left. So that's why you see oscillations in this IR dynamic itself, because at finite voltage, there is some supercurrent flowing through the junction.
Okay, thank you. I think Manoranjan has a question.
Yeah, Mano, please go ahead.
Yeah. Very nice talk and very interesting. So I have a very general question. That these superconducting junctions, I mean, what is is there any quantum effect? I mean, or because most of these equations are classical in nature, and so basically, is there a quantum effect is completely washed out?
In these junctions, these are dissipative in the sense that Rn is inevitably always there. So Rn is not right, a few ohms.
Yeah.
The normal resistance, right? So in this case, getting to the quantum regime, or rather exploring, will not be that easy, because the dissipation will, I think, will win. So in conventional Josephson junctions, you have a lot of quantum regime. I hope you're familiar with it. Are you?
Yeah.
Right. So this one, there is no quantum per se. I mean, no application in that sense which has been explored for constrictions. No.
Okay. Thank you.
I have one technical question here. Usually in conventional Josephson junctions, you are separated by like two superconductors are separated by like insulating layer or just some even air, I think.
Right.
Here, why you need weak links? I mean, without them also you can have your.
So this was something I reviewed in the beginning, because if you see this aspect, that Josephson effect will be there only if you have some minimal critical current.
Okay.
You will not be observing this effect at all if you go to very low critical current devices.
Okay.
So in order to in order to make Josephson junctions with good measurable critical current, if you use insulator, then you will need a large junction.
Okay.
Which leads to capacitance inevitably. But if you want smaller junctions so that you can make very tiny squids, then you have to work with constrictions and things like that.
Okay, this constriction material, whatever you have, it's the same niobium, right?
It's same niobium. It's just that, yeah.
Then this is also a superconductor. So then how you are making it non-superconductor? By sending more current?
No, it is a superconductor only, but this device acts as a Josephson junction. So this can be argued with Ginzburg-Landau theory, I must say. So that's where I said that this part is reviewed in this one of the papers, let's say. It's a simple physics, I can tell you, right? If you write the Ginzburg-Landau equation for such a simple constriction, if the constriction size is comparable to the coherence length xi, you find out right away that the critical current of such a constriction device will satisfy exactly this relation.
Okay. So then I have a question about this measurement limitation.
Right.
So with this device, so what would be the temperature range that one can measure of any like nanoparticles or anything?
So we will not cross TC. We cannot. So typically we do such measurements below 4 Kelvin in our setup.
So
Okay.
is it possible to, by changing the sample, like, Josephson junction material to some
Right.
other magnesium diboride or something like that?
People have made with high TC superconductors also. There is a group who is making high TC microsquids kind of stuff, okay,
Okay.
where they get a access to wider temperature range. But I think the sensitivity in those devices is much poorer as compared to conventional junctions,
Okay.
conventional superconductors.
I mean, magnesium diboride is also a conventional superconductor, isn't it, in one sense?
Yes, MgB2 is conventional. So
Yeah.
I don't think anybody is working with MgB2 microsquids right now.
Yeah. So this is also a BCS
No.
type superconductor.
Right. But I don't know the fabrication details, and I don't know what are the other parameters like critical current and critical magnetic field. What
Yeah.
is the HC of magnesium diboride? I don't know.
Yeah, I don't know, but TC, I think we all know it's up to.
TC is good. So HC will not be too low either, but HC,
Yeah.
it's a type 2 one. So then one has to see HC1 should not be too small.
Hmm.
That is one of the things, I
Yeah.
guess.
Then,
Yeah.
yeah. Yeah. It's
So,
really nice. Yeah.
yeah.
So then, okay, I have one general question, that in what sense this is, these micro squids are better than regular conventional squids?
They are not better, but they are serving a different purpose. In the sense, what I didn't discuss in great detail, like so in conventional squids, you are coupling the sample magnetic moment very indirectly. But in this case, we make a small squid and we put the particle right there, which is the case I showed you some of the
Yeah.
SEM images. Then the coupling is much better as compared to this remote coupling,
Yeah.
and then you become very sensitive. So you can sense magnetic movement of very tiny particles, which you cannot sense by this remote technique.
Yeah, that's what I also like realized. Even
Right.
tiny amount of sample also can be measured. We don't need
Correct.
to put a
Correct.
lot of
Correct.
material.
Right. So there are groups who have claimed that they can have a sensitivity which is more like a single electron's magnetic movement,
Okay.
that kind of sensitivity. But I don't think that is correct, but they claim that way.
But
Okay.
what
That's nice.
temperature can you go
So
to? I mean, to see the like in this microsquid? Last question, sorry,
Lowest,
Seti. Yeah.
I think it's the same question.
so temperature we go like we are limited to about 4 Kelvin
I
Yeah.
mean, that's the
from the,
maximum. Okay, okay.
Up to TC.
that's right.
TC of the material.
So typically 4 5 Kelvin we can still operate or below, but above that I think we will have problems.
Okay, okay, okay.
Yeah.
Sure.
So any more questions? Okay, if that is the case, then let's thank Professor Gupta once again for his nice presentation.
So I have stopped this. Huh?
Yeah, so
Okay, I can stop sharing, right?
you can stop sharing. Yes. Thank you, Professor
Okay.
Gupta, for accepting, and despite being like, diagnosed with COVID and then still and giving us such a nice presentation.
Thank you. Thank you so much for having.
Okay, hope to